Welcome to my personal training studio. I am just finishing up some cardio and waiting for my next client to show up. But I did want to give you an idea of what you're going to see in the next few minutes of this recording. And elements of physics play out every second of every session that I do with my clients. It's a matter of recognizing it, and it's pretty cool going back and watching these particular exercises and being able to pinpoint exactly what patterns of motion are being executed in these exercises. So the goal of this lab was to be able to recognize and explore patterns of motion witnessed in nature. So in this case, it's uniform and non-uniform during the processes of speeding up and slowing down. So on a daily basis, I ask my clients, to perform exercises that include patterns of free fall, uniform motion, projectile motion, and my goal is to show you examples of these exercises and transfer those to Logger Pro and graphically present those, and then compare those graphs to the ones that we produced during class time. So ultimately, I'm just trying to connect my daily life with our lab time activities and prove just how prevalent physics is on a daily basis. Let's get rocking. So this was the example that was given in lab to exhibit uniform motion with a constant velocity. Let's take a look at what this looks like graphically. This was the position versus time graph that was produced to show the car moving forward and back. The first line moves upward in a uniform motion in a positive direction with constant velocity. This is evidenced by the slope of the line, which is that first one at the top. It says it's a positive 0.6504 meters per second. The car then makes a quick stop at the top, which is evidenced by that straighter line at the top of the graph. And that displays a velocity close to zero by a slope of negative 0.09. Upon changing its direction to go backward, the car moves in a uniform motion in a negative direction, as you can see by that slope of a negative 0.7559 meters per second. So if the absolute values are taken of both the forward and the backward slopes, they're relatively close to equal, thus showing the uniform motion in both directions. Let's take a look at how that transfers to motion in exercises done in the studio. So here's my client Rachel performing a lateral band walk. This isn't a perfect example of uniform motion because of the changes of body position, but the idea is that the velocity is constant to ensure proper tension of the muscles throughout the horizontal motion of the exercise. Let's see how that plays out graphically. So here I've got a position versus time graph for Rachel's motion. We've got the positive direction with constant velocity with a positive slope on that first side of 0.1345 meters per second. The change in direction going down in the negative direction with a negative 0.1642 meters per second. I do run into difficulty properly graphing the change in position, so the top of that graph isn't nearly as straight as it should be, as it shows a slope of negative 0.1461, and it should be closer to zero. So I'm going to attribute that to the fact that it was a little difficult to track her movements correctly in Logger Pro. Let's see if we can find an exercise that more clearly shows some uniform motion. Here my client Mike and I are performing a high plank and rolling a medicine ball between us to work on anti-rotation and stability skills to strengthen the core. I track the motion of the ball in Logger Pro in an effort to better illustrate uniform motion. This is the graph I produced following the path of the motion of the medicine ball roll. It proved to be a much better example graphically of uniform motion. The velocity is relatively evenly distributed between the points of motion, and you can see the slopes of both sides, negative 0.7684 meters per second and a positive 0.7287 meters per second. When the absolute values are taken of those are relatively similar, proving uniform motion. And then the quick stop where the ball changes direction is shown at the bottom, where the line is much straighter, and that's proven by the slope of negative 0.003675 meters per second, which is much closer to zero than the previous exercise graph. This was the position versus time graph completed to exhibit the motion in the y direction, which was shown by the previous video. That video was given to us in lab. The position versus time graph shows the ball being both tossed up and coming back down from a time of 0.4 seconds to 0.7 seconds. As the ball ascends, it is moving upward in a positive direction with velocity that is specific to each point in the graph, since it is slowing as it nears its peak height. The slopes must be taken at the tangent of each point to determine the instantaneous velocity. At peak height of time of 0.7 seconds to 0.8 seconds, the ball displays zero velocity during its brief rest at the turnaround point. At 0.8 to 1.2 seconds, the ball descends in a negative motion with instantaneous velocity. This is demonstrated by the fact that a curve must be used to fit the path of motion and not a line, as seen in those previous graphs. Let's see how that plane of motion transfers to the studio. I had difficulty trying to format the previous vertically shot video of my client Chong performing a ball throw, so I had to ask my client Mike to perform it during his session. Let's see how this non-uniform motion plays out graphically. Unfortunately, this Y position versus time graph of Mike's ball toss is much less accurate in presenting non-uniform motion. This is due to the fact that I lose the ball from the frame at its peak height, which is displayed from the flat portion at the top of the graph. And Mike also catches the ball far too soon, so the full descent of the ball as it speeds up toward the end isn't shown. However, I did fit the parabola to the ascending portion of the graph and then again to the descending portion of the graph up to the point where he catches it. Between those graphed areas, you can see the instantaneous velocity of the ball as it moves through its path along the y-axis, slowing down as it ascends and then again speeding up as it descends toward his hands where he catches it. This displays the relationship between velocity and time of the ball as it moves through its path. This is the ball from the initial video that was given to us in lab time. The slope of the velocity graph and the upward motion of the ball from 0.45 seconds to about 0.55 seconds is negative 9.727 meters per second squared. This shows that the velocity, while positive, is decreasing as the ball ascends. The point where the graph crosses at 0.55 seconds is where the ball is at rest and turns around. At 0.55 to 1.24 seconds, the slope is negative 7.362 meters per second squared, and the velocity, while negative, increases as the ball falls to the ground. Let's see how velocity plays out in Mike's case. We can see again that this exercise provided a poor example of non-uniform motion, at least graphically, and that can be blamed on both my camera skills and my lack of instruction on how to properly catch the ball in order to capture the full trajectory of the motion. However, we can still get some useful information from the graph. The ascension from 0.8 to 1.1 seconds, it shows a slope of negative 7.779 meters per second squared. Like the previous graph, it shows that velocity, while positive, is decreasing as it ascends. The point where the ball crosses the line is long and flat, which tells us really nothing because during that period it was lost from the frame, but we can assume that it's reaching its highest peak on its way down because that short descent from 1.4 to 1.68 seconds shows a slope of negative 6.075 meters per second squared, which shows velocity while negative increases until Mike catches that ball. Let's now see one other exercise that involves motion in the y direction.
Ready? Just like this? Just like that. Wow. Last two.
So here's the y position versus time graph for Craig's exercise. And note that this exercise has two stop points as evidenced by the longer, straighter portion at the bottom of the graph and the second, slightly flatter area of the graph to the upper right. Again, I had to fit the ascension and the descension with parabolas, which is indicative of non-uniform motion. But the lack of consistent body mechanics makes this position graph really less pretty since the cursor moved along at really odd intervals. But the correct speed and direction of the ball out its path can still be recognized. Here we have the YT graph for the basketball shot video given to us in lab. If you'll notice, the projectile path is parabolic due to the constant vertical acceleration and constant horizontal velocity. This is now the XT graph of the basketball shot, displaying the linear relationship between position and time. It shows the constant velocity of the horizontal component. Here's the velocity graph for the basketball shot, which is at a slope of negative 0.04755 meters per second squared, pretty close to zero, which points to the constant horizontal component present in projectile motion. Here is the y velocity graph for the basketball shot. Vertical and horizontal components are independent of one another in projectile motion, and the vertical component of velocity is constantly changing and zero at the peak, seen here in the graph by its crossing at roughly 0.65 seconds. This exercise offers a great graphical representation of the projectile motion in the y dimension, showing parabolic fits in both directions as velocity changes throughout the course of the arc, stopping quickly at the top to display zero velocity. Here's the XT graph of the ball exercise, showing the linear relationship of constant velocity to time in the horizontal component. The VY graph of the exercise includes all of the parameters mentioned before about projectile motion. However, it's a bit harder to pinpoint the exact moments of slowing down to zero velocity at the top and then increasing on its way down since my client catch and throw at different positions. So concrete points of stopping the cursor during graphing was difficult. However, as you can see, the ball goes through its path starting slow at roughly 0.2 seconds and closes into its peak height where it crosses the line at 0.6 seconds. It then speeds up as it comes down to be caught at the completion of the exercise at roughly 0.9 seconds. I was hoping to draw a connection between what we're learning in lab and my job as a personal trainer. So by comparing the graphs from every activity, I was able to show how uniform and non-uniform motion and the subsequent relationships of position versus time and velocity versus time make up the very foundation of some of the most commonly used exercises in my profession. But I did know that creating clear graphs was a challenge. I'm going to attribute that to body mechanics. So I'm going to think that it's going to be really exciting to go further into the study of physics, to be able to show how all the elements in physics, not just kinematics, play into the execution of human movement.